Hey guys, how's it going? Derek Craig here with another oilfieldbasics.com Discover podcast. This is episode number 64, and today we're going to be learning about a little bit of an intro to production engineering, but just and beyond that, we're actually going to be going into modeling and kind of getting a feel for that territory and what all it includes and different software that's used and different techniques. And we've got Utkarsh Sinha here today to discuss that with us and walk us through that. And if this is the first time you're listening to the podcast, welcome. This is the podcast where we try to learn something new about our incredible industry on every single episode. So glad to have you. Just a couple quick announcements I wanted to mention before we dive into this particular episode's content. First off, just wanted to say that our internship application is up by the time that this is released. So if you know somebody who's looking for a job right now and they're still a student, or maybe they got their internship rescinded or whatever, there's a lot of students out there right now who are looking for opportunities to keep learning. And I invite them to go check out the application and apply. So it's going to be open for a pretty short window just because we're late to the game on this. We want to get the program started up here late May, beginning of June at the latest. So definitely send any applicants our way very soon. So check that out, oilfieldbasics.com. The links are all going to be there, and also on our social media, also, especially LinkedIn. So you can find it all there. Another thing I wanted to mention too is that, again, by the time this is aired, we've got a new course called the basics of complete frac chemistry, I think is the official title we're going with. I'm about to publish it tonight, actually, the day that we're recording this. But anyway, so that's going to walk you through a lot of the basics of the chemicals that are used in frac operations, especially here in the United States. A lot of us are probably familiar with the names of, but maybe aren't so familiar with, their basic properties, their selection, how you select and when you use them, and also even some different testings that you can do to make sure that all the chemicals are playing well with each other. So, and actually the lady that authored that, Tania Galindo, she was actually a previous podcast guest. So she previously talked about friction reducers, and she's got a whole lot more content coming down the line here in the future. So definitely check that course out. Like I said, there's going to be a lot more topics coming down. She's already talking about doing a course specifically on water in regards to completion. So she's got a whole lot more ideas also too. So keep an eye out for that. Definitely go check that course out if you're interested. Like I said, it's also up now at oilfieldbasics.com. So, and lastly, I guess we'll end with a real quick positive note here before we jump into this. I did just start to see some posts today coming through the wire that maybe the new oil forecasts for the rest of the year are a little bit more a little higher than what we had previously been expecting. So maybe a little glimmer of hope there that we see a recovery quicker than what we were alluding to even on a couple podcast episodes ago when we were talking about the industry-wide survey that was sent out. So we'll see. We'll keep an eye out for that. Hopefully some more good news coming down the line in terms of oil forecasts and pricing. And without further ado, let's go ahead and start diving into the topic. Like I said, today I've got Utkarsh Sinha with me here today, and he joins me. How you doing today?
I'm doing good. How are you doing?
Pretty good. And we actually just finished recording a little video interview for our YouTube channel, specifically on giving some advice for international students who are looking to get jobs, and just helping them understand the situation, different things they can do to get ahead, and resume tips. We covered a whole bunch of stuff. So definitely a very cool background. I'd love to hear more about what you do and what all you have your hands in here.
So I work as a production engineer for a service company that gives in-house wellhead compression service. Now, this is a bad word because it's long and complicated, so I'll break it down easier for you as we go further. But basically what I'm responsible for is modeling the well with natural flow and with several artificial lift methods, including gas lifts, ESPs, and sometimes we also have to deal with Pagel and Gapple, which is plunger-assisted gas lift and gas-assisted plunger lift. And right. We model less on that one, but we do some sort of maths on it, and there are some in-house methods. So I wouldn't, of course, go through the maths, but I'll give a basic introduction of artificial lifts. And yeah, wellhead compression service is also basically a artificial lift. As we go further, I'll explain what it does. It's easy, not that difficult.
Right. Definitely a lot of stuff to talk about here today. And the Pagel versus Gapple argument's always a fun one. It seems like every company like has their own preferences to how they view the distinctions and what they call it and whatnot. But
yeah, to be honest, there's no clear distinction
right.
on that one. So I would not say anything to confuse people that way, right?
Right. So definitely going to be a pretty good introduction here to some production engineering topics, especially for someone who's maybe not as familiar with the production realm or even in the engineering part of the production realm. So, but with that, before we dive into that though, let's talk about, want to get our viewers caught up too with your particular, like your educational background. You've got your hands in a lot of different journals and publications that you do.
Yeah, well, accidental, but let's talk about it. So I did my undergraduate from India. Those of you who are from India may be familiar with VIT University. So I did my undergraduate in chemical engineering from India. And then after my chemical engineering, I directly came for my master's without any work experience. But I had some of the good internship experience to get my hands on in petroleum, basically. And then after coming here, I did my master's from University of Houston in petroleum engineering from December 2016 to December 2018. And my thesis was around the PVT correlations for heavy oil, pressure, volume, temperature, basically fluid phase equilibria. And my whole work till now, whatever research I have done, is all around application of machine learning in PVT, using PVT for complex high asphaltene oils, heavy oils. And awesome. It's all around PVT, so it has very less to do with production. But yeah, that's also fun actually. PVT is so much fun.
So, there's definitely applications of production for sure, and I'll say too. For
even in reservoir. I mean, anywhere where you use the formation volume factors and gas oil ratios and viscosities and whatnot. But it has application. But then I was in depth there, so you don't need that much depth probably here. But
maybe we can define some of the terms here later. But
also sure.
I'll say too, for anybody who's just starting to listen to the show, the last podcast episode was actually on data science, also with the focus on production operations. So check that out too. It's really cool that we get to record these episodes back to back and release them back to back. I think it definitely add context to each other.
Sure, that's great. Actually, data science is everywhere nowadays. So
for sure.
So I published some papers in some of the leading journals and conferences out of it. I still do actually. I still work in my free time, in my spare time, with my advisor, and I also work as a technical reviewer for Journal of Upstream Oil and Gas, Journal of Chemical Information and Modeling. So I help the editors decide whether or not a publication should be accepted in my domain, of course, by reviewing, and as an editorial advisor of Journal of Upstream Oil and Gas. So these are like
awesome experiences. You wear a lot of hats.
Trying to,
Right. Yeah, no, definitely. I'm glad to have you on the show today, and I know we got a lot to cover, and definitely the guy to talk about this here. So let's, I guess, start with the basics here, and it was specifically kind of production engineering 101 here. I know you got a couple of different modeling things that we want to go across, different types of artificial lifts. So I'll let you pick up where you want to start.
Okay, so let's start with the nodal analysis, which I guess most of our audiences in petroleum engineering, and especially who have a background of production, must be familiar, but I'll start it from the very basics. So there are two parts. So whenever you talk about flow, there is one thing called inflow, from where the flow is coming, and there's one thing called outflow, where you want to send your flow ultimately to. So what happens that in a formation, your inflow is coming from the reservoir, right, which we all know, and your outflow is along the tubing, which you can also call as well, up to the wellhead, which is your tubing head if you have packers and you're only producing through the tubing. So you have, since I told you have inflow and you have outflow. Inflow decide how much maximum you can have at that point, right? That point, the conditions at that point and your inflow condition combined together will tell you how much maximum of flow you can have up to that point. In very simple words, of course, there is a maths into it. And then that point, conditions at that point, and the condition at the top, which is your wellhead, decide how much you can send from that point. So basically, if you see, this point is a common point where you have the inflow and outflow both, and it's known as bottom hole. It is known as bottom hole, and what happens inside the rock, inside the formation, inside the reservoir is basically known as inflow performance relationship. So now you understand why this word inflow comes, because it's the inflow to that bottom hole point, or IPR, famously known as IPR. Inflow performance curve, inflow performance relationship, whatever way you like it. And then typically your tubing, even if it's deviated, mostly the tubing parts are going to be vertical. So you call it vertical performance curve, or vertical lift curve, or vertical lift performance, VLP, very famous name, and VFP, vertical flow performance. Or you can call it in simple word, outflow curve. I like to call it outflow curve, because need not to be vertical, but it will always remain outflow. Now, when you talk about nodal analysis, you must have seen that diagram many times, that if it's pure liquid, then it's a slanted line coming in, and then there's another line intersecting it at some angle. So one of them, of course, called as IPR, and one of them VLP, and the intersection point is known as the bottom hole flow rate and bottom hole pressure, which is like the maths part of it. But what it is actually what I've told you, that point is common. So, you have a solution to two separate equations at one point where two lines or two curves intersect, right? If two curves intersect at a certain point, their coordinates should satisfy both the equations. So that is what it is. And in terms of physicalities, if you look in terms of physical science, what it is that in that point, how low it is in terms of pressure decides how much more you can withdraw from the formation. And if it is too low, so that the differential pressure between that point and the top point becomes really low, then maybe you have the capacity to withdraw, but you don't have the capacity to lift it till the height of the entire column. And what you eventually start doing is your liquid after a certain extent, its velocity becomes zero and starts falling back, and your well becomes static. And that's when your bottom hole point becomes static reservoir pressure.
And this is one thing too. I've known some people that get confused with saying, that's a dead well, or that well is dead, or that well is loaded. And this is exactly what we're talking about. So it's nothing physically wrong with the well itself. It's just to the point where it can't flow on its own. It's completely static.
Yeah. For example, I can tell you, if I keep a very high pressure at the top, let's say 700 psi, I know it's dictated by the separator pressure. Now I'm choking due to some reason, and I'm keeping 500 psi, 700 psi, right? For any reason, let's say I'm choking it at the wellhead, right? Now my well will start loading very quickly because my velocity will be less than the critical velocity, and as soon as it starts loading, it will start building liquid column, and at some stage it will be dead. But is it the well is bad? Is it my reservoir is bad? Or am I a bad production engineer? The third one is the right answer. I'm a bad production engineer, because it's like basic Bernoulli principle that any flow is dictated by the differential pressure. So if I don't keep low pressure on one end, and I already have low pressure on the other end, how will I keep the differential, right? So the more is the difference between the two ends of the pressure, the better it is. So
yeah, and just a couple things I want to tack on with that too is that obviously the 700 was just an example too. So I don't want someone who's to think 700 is like the magic number at what 700 psi is the magic number at which wells load or anything. But then also
no, it was a general number.
Yeah, for sure, definitely. But yeah, definitely all great.
But I can tell you the magic number that people have typically on their wells. They have 200 to 250 psi of wellhead pressure, which is 200 psi of separator pressure. So if they don't choke them, that's typical.
And definitely going to be very dependent on obviously what you're flowing into, like you said. So obviously right off the wellhead, the separator, but also to line pressure, right? Typically is what would be after that. So that's the largest.
That plays a very big role actually. If your line pressure, if you're sending the facility very far, then you would want to have bigger pressure so that you don't stop the transportation. You're right. So that is true. And
then the other thing I wanted to mention too is that obvious, the the pressure of the reservoirs, the
bottom
downhole
hole,
pressures are all
bottom
going to
hole.
be, yeah, all going to be different. And one thing too, so someone who's trying to figure out modeling and the things that we learn in school and whatnot, and as you're saying, like it's not relatively complex to do these calculations and know when a well should almost exactly when a well should start loading on itself. But one thing that we don't always seem to have is the actual downhole or bottom hole pressure, as you're calling it. So I guess what's your kind of thoughts for people? I mean, you can run downhole gauge, you can do like fluid level shots and whatnot, but I mean, what's your general thoughts as to kind of knowing approximately what that is, because that's a big part of nodal analysis, correct?
Yeah, all that was true. So what typically happens, let me tell you, like we as production engineers don't know what is the bottom hole flowing pressures when we get the data. I can tell you in details what we get typically is the production rates, the tubing head pressures, right, in a naturally flowing well, okay, because it's a simpler system. What we get is what is approximate reservoir pressure, which is actually easy to measure. There are several ways of doing it. One is like well shut in, and then when your well is shutting, your static pressure of the fluid column becomes equal to the static bottom hole pressure, which is average reservoir pressure. Anyway, we get approximate value of your reservoir pressure, and we get the construction of the downhole assembly and your deviation surveys if it's not a perfectly vertical well. So I would know
like
where.
Never are.
Yeah, typically, yeah, they never are. But talking about a simplistic system, so how long is your tubing, what is the geometry of your casing and tubing running along, and what is the depth of your perforation, like if it's an interval perforation. But many times in modeling, we don't even make perforation the way it is in real. We take just one point of fluid entry, and that replicates the whole interval, and 5-inch or whatever length you have of the perforations, you just take single point and it replicates all. It's in feet, several feet sometime, and you have to, and it's sometimes less than a feet, but in several intervals. After every 10 inches, you have a separate perforation. Depends on the formation, right? Especially if it's horizontal. So we take a point, but this is all we get. Now, what we do is we try to match the production rates in the field by adjusting the productivity index, which is a proxy to all the skin factor, the permeability, the net pay, in a way, all the properties of your inflow, which is your formation. And we try to tune it to match the current production rates in field. Now, many times the students ask me, if you're matching it and tuning it, what is the point of modeling? Because you already know the rates and you're matching it. So yeah, if you're modeling it in native state, there's probably no point. But let's say my tubing head pressure was something, right? It was 250. Now I want to check what is the impact when I reduce it to 150. At that time, the properties of my inflow don't change, right? Only my tubing head pressure changes. So if I have tuned it and found it, I can use the same value in the model and find the impact. So it's like taking a real model, history matching it, and then playing sensitivities around it. You can change the tubing depth, you can change the wellhead pressure, you can change, you can put an artificial lift and see how it is performing there. So, like taking a standard real performing model is only possible when you tune it to how it's performing currently, and then you make tweaks in that and see how
run the different cases that you want to see.
Yeah, exactly.
And one thing you mentioned too was kind of that most people probably know what permeability and porosity refer to, but skin factor, you kind of want to just quickly define that. And then I'm curious to also know a little bit more about your thoughts on modeling kind of real life versus school, the different challenges,
Sure.
From textbook to real life.
Sure. So skin factor, basically the easiest definition I can give you is it's a sort of resistance. It's a sort of resistance to your productivity. And the lower it is, the better it is for your well productivity. If I go into the details and maths, actually it can probably be complicated, but just take it as a resistance, one of those resistances.
And even just just like formation damage is basically another quick way to summarize
it's a formation damage, which is a resistance to your inflow.
Yeah. We're just assuming how much is damaged, right? Because how do we really know?
Exactly. Extent of your damage, and there's a math around it, which depends, of course, on the geometry of the formation, and of course on several factors other than that. And then if you have sands coming in, there's a different animal if you start having sands, etc. But it's a formation damage, which is kind of a resistance to your inflow. But it's only affecting the inflow, which is a very important point. It doesn't, your skin factor doesn't affect your VFP. It only affects your IPR,
your
inflow
delivery,
performance curve.
the surface, well
delivery.
So real life versus textbook, what you got for us?
So real life, I guess, any of the production engineers who are going to school right now must be studying Darcy model of inflow performance, basically, where they have to put all the net pays and then all those things, and then several models, like for example Vogel model for two-phase flow, singular phase flow. Until it's singular, it's a linear line, then it becomes a curved line, and then you have gas, which is typically parabolic, etc. And they must be solving very difficult equations over there. But trust me, when you work, you don't have to do such complicated things. You will have limited data in hand. You need to understand how much information you can take out from those data. You typically won't get things like what is the permeability, what is the net pay. Also, you must be knowing permeability is not a constant number, so averaging anyway wouldn't give you the real life representative. That's why I said we use a proxy called productivity index, and we tune it to the well productivity index. And so in school it's a very difficult thing based on maths. The maths is very difficult because you have to solve several equations, put things here and there. In real life, difficulty is not in terms of your maths, but the difficulty would be in understanding. You need to understand like why something is happening. For example, if I have an orifice in my tubing, why do I have it? Or if you must have seen several times that people start producing from the annular region and they put a tubing plug and they're not producing through the tubing. Why is that happening? Is that happening because they're enjoying it? It's fun to produce from the annular region? I don't think so, right? Tubing is why they are doing that. So it's more about understanding those things. For example, I can tell you one of those things. If I have a orifice in my tubing, what I'm doing is I'm trying to increase the velocity. I'm trying to give an orifice effect and increase the velocity. And what that velocity does is, if I want to avoid liquid loading, I want to keep my velocity of gas above the critical velocity of Turner or Coleman. Turner typically we use for modeling. And that increase in velocity will probably increase it above the critical velocity calculated from Turner. And once that velocity is increased, then you will actually have no loading and you can take all your liquids to the surface. Loading means your surface liquids start falling back to the surface.
Right. And that's the primary reason why we install tubing to begin with, right? I mean, it's a whole lot easier to flow and get that critical velocity in 2 3/8 or 2 7/8" pipe as opposed to 4 1/2 or 5 1/2".
Exactly. And why do we produce from the annular also? The reason is that sometimes when you see that, okay, my reservoir has very high pressure right now, so I wouldn't have anything like loading or anything. I wouldn't have any problem, but I'm not producing it to its full potential because what I'm doing is the productivity of the well is very high, the reliability is very high, but because of small diameter, I'm exerting a lot of back pressure due to friction. So I want to open it to a bigger surface. I mean, it's like one of your taps. If you have a tap with a lot of water coming in, you would want a pipe with a bigger diameter. If you have a tap with little water coming in, you would want a pipe with a smaller diameter. So it's all real world problems.
Does the fire department just use one hose? So
you don't have one hammer to knock down every problem.
Right. No, definitely good perspective to have, though. In terms of I know we got a whole lot more topics and stuff to cover too, but so you mentioned inflow performance, inflow, modeling your inflow, your outflow, so IPRs, and then vertical flow performance curve stuff. Is there anything else that you wanted to just throw out there before you?
I guess that's it for the basic introduction, and
I'm sure there's more. No, that's fine. And I think this would be a good transition for us too, because we've talked about liquid loading multiple times throughout all this, and
Yeah, and
that's
I told you how you check basically the liquid loading as well. So
yeah, exactly. And a lot of the modeling and stuff that you talked about too is like IPR and like well deliverability and everything like that. A lot of that is basically from a flowing well, right? Like no artificial lift, right? So let's start.
yeah,
Let's dive into artificial lift here now and talk about. So obviously this comes into play, right? So your well starting to load up on itself. It's not able to keep that critical velocity, and then so you're going to need something to help it out. So that's like the pump jack,
sure.
that's the plunger lift, that's the gas lift, right? So all these things,
Gas lift
and
and
so
ESPs.
give us your 2 cents on all these, and I guess what
Sure.
modeling is associated with them and what's different.
So yeah, talking about artificial lift, like Derek mentioned, one of the things is of course liquid loading, which is in typically in gas and condensates. You'll see that more, where you can take your critical velocity above. Another thing is also about production boosting. For example, I'm getting certain production rates, but I know I have the potential to make it better. So I would always want to, like in real world, none of the wells produce naturally all the time. You put them on, like it's a standard practice, you put them on one of the artificial lifts. So over here, I will talk in details about gas lift and ESPs because that are, I guess, the most common ones that we study in school. And I'll give you a bit of introduction on my domain, which is wellhead compression. And
For sure, yeah.
I guess it would be good for this particular podcast because students would be able to relate with gas lifts and with ESPs quite easily. So we need is artificial lift. First of all, like I said, either you're not able to produce, and first thing first, what curve is affected by your artificial lift? That is a very important question. Like I said, skin factor only affects your IPR, right? More the skin factor, the lesser you can have the maximum rate in the IPRs, etc. Same way, what artificial lift would affect would only be the VFP. It doesn't affect your IPR.
So it's more the outflow part, right?
Yeah.
Not so
It
much the
affects the
inflow from the
outflow part,
formation.
not the inflow part, exactly.
Right.
And which is understood because you don't bring your artificial lift inside the formation. Where do you bring it? You bring it at the bottom of tubing typically. So how would you make a change in the formation properties? Because it's being driven by the properties of formation, right? So
and even that end of tubing is a big is a big decision in itself too. Like how close can you get it down to the formation?
You don't want to go that deeper. Typically, like for say gas lift, we keep like 150 feet above the packer height, and packer is already a bit above the tubing. So that too depends on the well actually. So I'll cover, and probably by the end of the podcast, people would know how deep you can go, etc. So after the constraints.
Awesome.
So let's start with gas lift. So first, very general introduction. So for a single point, I wouldn't talk so much about unloading by gas lifts because that is something which is complicated and it has to be very specific to a webinar. But I'll talk about a flowing gas lift where
normal everyday operations with gas lift. Not so much whenever you first started on. Right. What you're talking about,
when you install unloading, right. Exactly, kicking off. And if you want, I can give you a bit of intro on kicking off. I've worked, but then let's see how it goes. So let's talk about a naturally flowing well, which I want to enhance, or a well which has started showing symptoms of loading. If I want to enhance that well using gas lift, what does it do? So you have a pressure at the casing head. That pressure will, that pressure minus the frictional pressure drop plus the weight of the gas, the pressure due to the weight of the gas, will actually tell you pressure at different point, pressure versus height in the annular column from where you typically inject. There are cases where you can inject from the tubing as well, but not so much as you inject with the annular region, from the casing head. Once you have those pressures, you'll have an injection point. What happens at the injection point? If you ignore the valve losses for a point, what happens is you're almost at your injection point, your tubing performance curve, and your casing head pressure gradient, they intersect. meaning that at that point the pressure would be the same. I mean, little bit difference due to the valve pressure losses, but almost the same depth, right? And what happens physically there, once there is once that point is reached, what happens through that valve, through that injection valve, there's a U tubing, and all the gases from the casing starts entering your tubing head. Once it starts reaching your tubing, what happens is because gas has a better tendency to flow, it will start taking the liquids up, or you can take it like this. The density is getting lesser as you have gas coming in there. And lighter column is easier to lift than heavier column. So that impacts your bottom hole flow pressure. Your bottom hole flow pressure comes down and you start flowing continuously with better speed. So it's more about lightening the column and using the speed of the gas to take your liquids at the top. Combined effect of both the things.
Yeah, I think it'd be important too to highlight the use of the packer in this type of a system. So for people who aren't familiar,
packer becomes So when you finish a gas lift, when you finish a well and you know that you're going to install a gas lift in the well, unless you want to do a gapple or paggle, you will have to keep a packer. In gapple and paggle, it becomes a different thing because then you don't keep a gas lift and the gas comes from the annular region and then comes at the bottom and then it re-enters through the tubing and starts lifting your, plunger. But if you don't want to keep a gapple or paggle, you need to keep a packer to make sure you don't have, you don't have your gas going right at the bottom and then coming through the tubing. You want all your gas to, seep in through that injection valve.
Yeah, and typically too, it's surface casing pressure, with a packer system is going to be higher, right? Because you're literally using a compressor to send this gas down the back, down in your side.
Yeah, exactly. It's going to be more pressure when you have a packer than you are injecting without a packer because you're having a constraint and you're hitting against a constraint. So yes.
Yeah, and if you didn't have the packer there, then it'd be going straight to increasing your bottom hole pressure, which would affect your inflow, right? How much is coming into the well, ultimately affect how much you can produce. So
you can have that gas even entering your formation and changing the dynamics all over, because you're exposing the bottom hole there. So in gas lifts, if you're talking about gas lift, you need to have a packer. It's very important. And what is the typical injection pressure in a gas lift? It's 900 to 1000 from what I've seen, sometimes 800 as well. But I haven't seen so many wells being operated above 1000. And you can take my word, 1000 is a standard high number. 900 would be more of a reasonable number, 900 psi casing head pressure or the injection pressure, whatever you call it. Also, you don't do it typically in heavy wells. You don't do gas lifts because of the reason that when your gas enters, you have this Joule-Thomson effect because of which a cooling is a reduction in temperature is produced at the point of injection. And if it's a heavy oil, it's already viscous, and with the reduction in temperature, it will get more viscous, so it creates problems for you.
It's a bit harder to lift. Yeah, for sure. And when we see these typically
you'll inject steam there, or you'll use ESP.
Gotcha. Yeah, and we see a lot of gas lift with higher rate wells, so it's becoming more and more common, or at least was in Permian, right? It was in multiple oil plays.
Yeah, exactly. So that is the case. But that's how your gas lift works. Some of the important things, what is typical injection rate seen? So injection rate, you don't have a lower bound in that, of course, but you want to inject till, so the curve is typically parabolic. And with parabolic, what I mean is if you keep on increasing the gas injection rates, there will be a stage where your well becomes so gassy that, the friction pressure drop becomes very high. And at that point, you want to switch to a rate lesser than that so that you can maximize your production. So if you draw a curve between your injection rate and production rate, there will be a point where where you reach the peak of the production rate. That is the maximum you want to inject up to. And if it's a low GOR well, you have anyway a constraint. Like from what I have seen, I haven't seen any well where the injection rates were more than 1.1 million cubic feet of gas, standard cubic feet of gas. So 1.1 is again a high number. Typically what I've seen is between 0.7 to 0.8 million of standard cubic feet of gas.
Yeah, and from a production engineering standpoint too, that also becomes, a very strong point of optimization, like, because that gas is typically, you're typically buying it back either from yourself or from your midstream partner, whoever's taking the gas, and that's expensive. And then also too, like you said, just because you're
it becomes
injecting.
Exactly. It becomes a very important part because first of all, you're buying it from a midstream partner. That is true. And if you're not, then you are using gases which are coming from basically there's a pad on which you'll have several wells if it's a gas lift. So you're collecting gases from other wells which are on, let's say, natural production for a while, and you are using that gas to inject, or you are using the gas injected during the natural flow and re-injecting, one of those ways. If you're not, if you're not getting it from outside, then you'll have to use the formation on that pad to collect that amount of gas. So yeah, in production modeling, it becomes a very important, because first of all, I'm hurting my well in terms of rates. Secondly, I'm wasting the gas, which I already have a constraint on in terms of volume. So it is one of the most important optimizations, and you would want to, keep your wellhead pressure in tandem so that you make sure that you make the maximum use of your gas rates.
Okay. Yeah.
Because you can support your wellhead pressures and gas rates by lowering wellhead pressures and injecting gas at the same time.
Gotcha. Okay.
So yeah, it's a very important optimization technique actually.
Gotcha. Okay. Yeah, definitely a lot of opportunity there with gas lift. And I guess like any specific, so I know we're talking about modeling and stuff, but I mean, is just kind of the standard modeling software used with gas lift also?
Yeah, so I have been using PipeSim all this while. People also use Prosper, but PipeSim both belong to Schlumberger, both are for production, but from my experiences, I can tell you PipeSim is quite good. But it's only for steady state flow. So if you are doing intermittent gas lift, that's when your system becomes very dynamic. That's when you'll have to switch to Olga, which is their transient and dynamic state modeling software, and you can do it. But you don't get to model intermittent as much as you model the steady state gas flow. So as long as it's steady state, PipeSim is a very good software to model. And what you need typically is how much you are injecting at. Either of the two. If you know the injection pressure, you can find out what is the injection depth. If you know the injection depth, you don't need the injection pressure, because you know that at this point you're cutting the tubing. So it's like giving one and getting another thing. So but you typically don't, you take optimum depth, you're given the injection pressure, you take the optimum depth and you're given the rates. And if you're lucky, maybe he'll give you the specific gravity of the gas. Typically, we don't get it, and we assume the specific gravity of methane.
Okay.
But it doesn't affect it so much, because the weight of gas anyway is not that much that it would affect. So.
Gotcha. Okay. Yeah. So I guess that's gas lift in a nutshell. So what you got ESPs also you wanted to hit on?
Yeah. I'll talk a bit about ESPs as well. So in ESPs, many things get important. First of all, I don't know if our viewers or our listeners are aware, but ESPs have a rate constraint, minimum rate and maximum rates. So one of the challenges with ESP that often comes is, let's say I want to boost so let's assume for now that ESP is boosting the production. So I want to make sure that my rate before I'm putting the ESP falls, above the minimum rate, which is for that ESP. If it doesn't, I wouldn't want to put that ESP. Secondly, so if my well is not producing at all, I would use a ESP which has a minimum flow rate of 0, liquid flow rate of 0. Okay. And time to time, you might also have to change, because let's say your formation was at a very high pressure and it was producing pretty nicely. So you chose your minimum that way. Now it has depleted after several years. Same ESP cannot work. So you'll have to pull out your ESP and put another one. Now, what does ESP do? How does it work? First of all, let's talk how it works. So what you do is your ESP is a pump where you have a combination of pump and motor, and it uses centrifugal force to support your differential pressure. So with what you had as your differential pressure, which was typically the difference between your wellhead pressure and the bottom hole flowing pressure at any stage, you get a delta P pump with that. And that delta P pump, which is the additional pressure coming due to the centrifugal force of your ESP, helps in building, that, like I said, the flow is dictated by the differential pressure. So if you're adding additional pressure there, you're increasing the differential so you can lift the fluids if you're not able to. And if you were able to, you can increase the rates. So like I told you, they give an additional centrifugal force, so you have an additional pressure besides the differential pressure that you already had, and that pressure helps you lift faster if you were lifting with certain speed, and if you were not lifting it helps you lift. So it's like an additional delta P that you're getting out of it because of the centrifugal force, multi-stage rotation, basically. And one of the things that become important with ESPs is that your formation should be very low on GOR. If the GOR is high, you need to have a bottom hole separator that can separate the gas out and send the gas in the annular region. How to select the size of ESP is also important because your ESP should be the diameter of ESP should fit in the tubing diameter, internal diameter, and the cable should be of the thickness so that it can go through the annular. If it's very thick and your annular space is very small, you cannot send the cable. But yeah, what you do is you put a downhole separator. If it's too gassy, you send the gas out through the annulus, and your liquid goes through the tubing, passing through the pump, which is above the separator basically. And and finally the two fluids, the gas and the liquid, could be recombined at the wellhead.
Okay. Yeah, definitely a lot of good insight there.
So
you have a lot of options.
Every well is different. So, but again, like I said, it makes a difference to your wellhead performance, vertical flow performance curve, and not to your IPR, like I stated for any of the artificial lift methods. So,
okay, gotcha.
So yeah, so probably give you a brief intro of what we do as a compression, wellhead compression technology. And
yeah, so where does this fall into it too? Where, I mean, like, is this just a lot of where I've seen wellhead compression is, wells that are still free flowing, or even, maybe wells that have plungers. Like, I guess what all applications would there be to, okay, this is a good candidate for just doing wellhead compression?
I would say any well would be doing well on wellhead compression because we have multi-phase compression. So if you have a gas compressor, which was typical case, it won't be able to handle liquids, and that's where you have problems. If the well has liquids, then you can't do wellhead compression. But with multi-phase compressors and our in-house technology, we have a very good. So I'll describe compressors in brief. It's one of those magical box where you have a suction pressure, and then you multiply that suction pressure several folds, and you have a very high outflow pressure, right? So when you put this magical box on your well, what you can do is you can suck at a very low pressure. What I mean you can suck at a very low pressure is your wellhead pressure can go to a very low value. And as you know, any well will show improvement in the VFP. The VFP will shift towards the right if you have a lower tubing head pressures. Now, how much that would happen depends on a lot of things. How gassy your well is, because what you're doing basically by sucking pressure from the top, you are removing pressure from the bottom as well, right? If there's a lot of gas, let's say you suck 100 pressure, and you don't, if there's sufficient gas for a liquid well, let's say, if you suck 100 psi from the wellhead, you might suck 200, 300 psi at the bottom. And if the gas is too much, then maybe friction comes. So you suck 100 at the top, you only suck 80 at the bottom. So, you need to have the optimum GOR for that, which is again mathematical and optimization. But my point is you're lowering the pressure at the bottom. Mm-hmm. And if your bottom hole pressure is lowered, that means you have a better flow, right? Because you go towards the right of the IPI, your VFP shifts right? So this is the concept. Now, where it works, is very abstract. You have to do a lot of that sensitivity analysis on several productivity index, several GORs, and you have to find and then also what is the tubing head pressures in any of the wells. If it is already 80, let's say, right, if the separator can come up to 80 psi, then I think it's already very low, because I said the standard number is 200 versus a well which has 500 because it's being choked.
Right.
So the concept is again the same. Like I told you, you reduce the wellhead flowing pressure, and when you lower the wellhead pressure, you also lower the bottom hole flowing pressure, and you increase your. Now, I'll tell you in brief the benefits of it. First of all,
Can I
in
ask you one
terms of
question too before you jump into the
sure.
benefits? You'd mentioned that you can't do it on a well that has basically in liquids, but you could put the compressor on kind of this gas sales side of the separator, correct? And you could still basically get the same result and be able to handle liquids.
Yeah, of course. I mean, you can attach it to a separator, and you can lower your suction pressure, and your separator pressure will be lowered that way. But typically, we don't want. If you have separator, it's good. But if you don't have, we don't even want separators because, see, earlier the arrangement was. I'll tell you what was the typical arrangement. I'm sure you must be aware you're in production, but just to reiterate on it, you had a separator, you had a certain separator pressure, which was high enough to send your liquids. And then for the gas stream, you had a compressor because of the frictional pressure drop. You want to accelerate the pressure and you want to send them in separate lines. That's how it was. But that was a gas compressor. When you have a multi-phase compressor, you don't even have to separate the lines of gas and oil. You can send them in a combined line to the gathering station.
That's interesting. Yeah. And that, do you see that being very common? I haven't really seen a company doing that yet.
I mean, we do that, and we are working with some of the bigger clients, like some of the biggest operators here, and they have really appreciated the work. So, it's all
definitely
happening.
Cut down on some costs field wide. If you can put it all together
that's
like
why
that.
you can suck at a very low pressure, because then what really matters is how much is your compression ratio. If you can suck at low pressure and still give the same outflow, then you're good to go, right? And the reason why we are able to do that is because we can produce a very high outflow pressure for a very low inflow pressure, right? We have that sort of construction, or that near isothermal compression is not a myth for us, right? So we are able to. So you cut short of the separator, and that saves you a lot of cost because you lower your. I'll tell you the cases where we lowered from the separator pressure, we lowered from 200 to 40, 50, 60 psi, right? And it's still able to give better than separator pressure, the outflow pressure. So transportation become easy. You don't have to separate the streams. At the same time, you're producing more. So it's multifold benefits. So yeah, this technology, not just us, it's coming up. This is one of the bigger revolutions. Probably you will want to check our pages to get good animations and videos for this Reach production solution. If you go to the page, we have several animations made for this.
Okay, very interesting. Yeah. I'm just curious too, like what's the compressors typically look, I mean, how do they differ from just a typical compressor so that they can handle multi-phase like that?
I mean, so without getting into the technical
high level, that's fine.
So a lot of things are proprietary here, Derek, so we cannot really it depends from company to company, and those are like in-house technologies. But what I can say is from outside you won't be able to feel the difference. Everything is different inside the designing, the designing parameters, what are the shapes, what are thermodynamic conditions, etc., that you keep for multi-phase. Because how well you can separate inside the compressor the two phases, basically, so that you can compress, because as we all know, liquid cannot be compressed, right? So you'll have to separate. How well you can do that depends on your designing parameters.
Okay. And then I guess like the output from the compressor in a sense is basically just, I mean, it's still all together.
Yeah. So it's about collection, separation, compression, and gathering.
Okay.
Inside the compressor itself. Yeah.
Okay. A lot goes on in there.
Yeah. Well, yeah.
Yeah. Okay. Sounds good. I didn't mean to derail you. I was just curious. So I think you were going to have benefits.
I guess people got the idea of it. Yeah. And if you use it with artificial lift, let's say like ESPs, or let's say gas lifts, what are the benefits? So benefits are like, as you know, that what would happen if you have a compressor, multi-phase compressor, and a reduced wellhead pressure due to that? You basically, the free gas comes from two sources. One is what you are injecting, right? One is where your gas free gases starts parting from the liquids, which is known as bubble point. So if my bubble point is 1,000 feet from, let's say 1,000 feet from my wellhead versus it is 5,000 feet from my wellhead, where do you think the flow would be more favorable? Where will be the better flow rates? Of course, where it's 5,000, because by the time it climbs 5,000, I'll have a lot of gas. So it will be a really light column, very favorable for me, right? And when you suck pressure from the top, what you're doing, you're sucking pressure from the bottom. So every point you're reducing the pressure. But bubble point is still a fixed number. So what is happening? Your bubble point is actually coming down. So this is how you already generate the gas from the liquid itself. So you would need less gas to inject. You don't have to inject that deeper as you were doing. And if you still persist on injecting at the same rate, you still persist on you also get a facility to inject deeper because your bottom hole flowing pressure has reduced. So pressure at each point has reduced. So with a given pressure at the top, if you're injecting at point A, you can go to a point B, which is deeper, right? So you have these benefits. Plus, one benefit is you can save on your gas injection volumes. And another point, if you keep everything same, the injection depth same, if I'm stubborn, I want to keep the same injection rate, I'm rich, I want to keep the same volumes, I will get amazing flow because two things are working at the same time. So overall, a lot of gas is there to drive my liquids to the surface.
Now, whenever you're basically just lowering the back pressure in a sense on the well, right? So
wellhead. Yeah.
Do you have any, whenever you talk about hitting bubble point, do you ever see it where it's kind of a reverse effect in a sense that it actually makes things worse because now you're dealing with maybe the oil is a little bit harder to move now because it doesn't have the oil or the gas with it? You know what I mean? Like, do you have issues with it from that side too sometimes? It seems like a double-edged sword, maybe.
I understood what you mean. So basically, you were saying that if I lower the pressure, what is happening is that the gas starts flowing on its own, leaving all the oil behind, right? So yeah, you typically wouldn't see that sort of cases because you are not making any change on your inflow parameters. You are making change only on one end. So what you are doing eventually is any point of time, if you see the static reservoir, static bottom hole pressure is still the same, which is like the maximum pressure bottom hole pressure can go up to, right? And at the other end, you have lower pressure. So your differential is always good to actually make them flow together in tandem. Only thing is sometimes like one of the challenges that I have seen personally is if your well is too gassy, you don't want it to flow at a very low pressure because of the frictional problems. So again, dropping the pressure is always a choice, right? So if you can mathematically model what is the optimum pressure you want to go up to, you can do that.
Yeah.
It's always a choice. I mean, I wouldn't want my well to suffer and still lower the pressure. So there's a lot of math done to it, but 99% of the wells, it works very well, actually.
Okay. Very interesting. And this is where I mean, this is basically what you do, right? This is the majority. You do a lot of modeling behind this. Yeah.
Yeah. That's one of the reasons. And of course, like we spoke about loading, so I would want to add in loading as well. What happens is if you reduce your wellhead pressure, if you see the correlation, your critical velocity is lowered because it's a function of pressure, right? So you lowered your critical velocity and you increase your flow rate because of lowering pressure. So you increase your velocity. So if you were below the critical velocity has reduced, your velocity has increased. So now you are above the critical velocity and you wouldn't experience liquid loading because of that.
Okay. Yeah, definitely a lot of options.
Yeah. So yeah, like I said, different wells have different hammers.
Right.
You gotta find the best one for the best one. But yeah, we work a lot in tandem with the other artificial lift technologies and works well. Yeah.
Gotcha. Yeah, no, definitely. I appreciate all your background on all this and just sharing the basic that we cover a lot of different topics today for sure. I know there's still a lot more on the table that could be discussed, but definitely a lot to soak in here for one episode. So definitely appreciate you and your time. Anything that you forgot you wanted to throw in here real quick before we wrap up?
Not anything major, but I would want to say that people who are really interested in developing their careers in production modeling, etc., should probably start looking for modeling resources many free trainings on the software. So the more you can learn it, the better it would be, because you'll be a full-fledged engineer by the time you leave your school. So just keep studying and try to attend one of those commercial software training. And yeah, good luck. I'm sure.
Yeah, for sure. Definitely. And if that's something that interests you from an engineering background, anybody listening, definitely check out some resources on that. I'm sure you can reach out to Utkarsh on LinkedIn or whatever. I'm sure you can point you in the right direction.
Yeah, sure. My email ID is also available there, so you can write to me there. And yeah, there are links to resources of production, some of the things that I have worked and got published from company side in the magazines, EI, etc. So you can feel free to stalk my LinkedIn and grab whatever information you want. And feel free to write me.
Awesome. Yeah, I'll drop the link to his profile in the show notes for this episode. So thanks again for being on the show. I really appreciate all of this. And thanks again for all of our listeners. Please be sure to check out OFO Basics on LinkedIn, our website, also for those new courses. And please be sure to drop a review on this podcast. So until next time, everyone, stay safe and healthy, and we'll catch you in the next episode.